So far, we've only ever found the area under a finite region, that is, has a firm left and right endpoint. They're not running off to infinity in any way. But what if we have some infinite regions? So for instance, what if we have something that looks like this? We have a curve crossing one of our axes, it's bending down towards the other, indicating that that is a horizontal asymptote, the x-axis is. Or maybe we have a shape where the y-axis is an asymptote. It doesn't really even have to be at the axis, it could be anywhere. But if we're to find the area under these curves, we can see that one of the sides is running off to infinity. And so it kind of is a challenging concept if we think about an area. It's length times width, or we've used integrals. But here we're going a length of 0 to infinity, or here we have a height of 0 to infinity. Will these give us still a finite area? We're approaching 0, but do we get there quick enough to say that that infinity doesn't matter? So both of these pictures, the answer is yes. These will have finite area. And so just like we've done in the past, we need to find those areas using integrals. But now because we are going to infinity, we're going to have to look at what is called an improper integral. And that is what we're going to look at in this video. We're going to look at improper integrals. So let's take, for example, y is equal to e to the negative x. Let's start by thinking about that picture. Well, e to the x, it's that infinite curve. Let's try to draw that a little bit better. Going through the y-axis at 1, and because we have the reflection about the y-axis, it's going to be decreasing and running off to infinity to the left, and it's going to y is equal to 0 on the right. And let's think about finding the area to the right of the y-axis here. Are we going to be able to do this? Yes. Now, as it stands, if we were to try to set up an integral for this, we'd have the integral from 0 to infinity, and that doesn't make sense. We can't just keep taking larger and larger values. We can't plug in infinity. So let's start by thinking about the area from 0 to some point b. Start by thinking about the area from x is equal to 0 to x is equal to b, where b is just some finite number. We're not defining what it is, but it is what it is. And so we could easily find that area. The area would be the integral from 0 to b of our function e to the negative x dx. But what we said we're really trying to do here is find the area of the infinite region, meaning it's going off to infinity. Well, what have we used that allows us to look at heading off to infinity? A limit. So now what we're going to do is to find the area to the right of the y-axis, take the limit as what we're saying, that upper limit of b, as b goes to infinity. B goes to infinity. We've already said let's start by saying we're going to just some value b, because that gives us this fixed endpoint, so we can find the area the same way we're accustomed to. But now what we're saying is really I'd like that b to continue to grow infinitely, so let's use limit. So now we can find this area under the curve as the limit as b goes to infinity of the integral from 0 to b of e to the negative x dx. So let's go and find this. So we'll take the limit as b goes to infinity of the antiderivative of e to the negative x is negative e to the x, and we're going to integrate that from 0 to b. So we'll have the limit, b goes to infinity, of e to the negative b minus a negative e to the 0. And so I'm just going to continue to simplify. Limit as b goes to infinity of negative e to the negative b plus 1. And now we're to the point that we need to take our limit. And so if we think about the limit as our b goes to infinity, well, the negative really means that the e is in the denominator. We would have negative 1 over e to the b power. And so as our b goes to infinity, that e is going to a 0. And so we're left with the limit value of 1. So what this tells us is the area from 0 to infinity of e to the negative x is simply equal to 1. All of this space here is simply equal to 1. So we took an infinite region, something that was spanning 0 to infinity, and we still were able to calculate an area because those y values were getting infinitesimally small the further and further we went out. So right here it wasn't quite equal to 1, but as we're adding those tiny, tiny values further and further out, that is getting us to exactly the 1. The 1 is exactly the area under the curve. So what we're using here are improper integrals. We have an integral where really what we're trying to do is we're integrating out to an infinity, or we could be integrating from an infinity, could do it either way. And when we do that, we still can get to a function value. Now, notice we didn't, and we are never going to plug infinity into a limit integral, and into the limits of the integral. We're not going to have it as the upper or lower number. We're always going to set up these improper integrals with this limit statement right here. We're going to write that limit statement in front to solve these improper integrals. So there's actually two types of improper integrals. Let's discuss those. Improper integral of type 1. Improper integrals of type 1. In these cases, the integration occurs over an unbounded region. And this was like the first example we just did. One of the limits of integration would be an infinity. One of the limits of integration is infinity, or negative infinity, so I'll put a plus minus there. That is like that example we just did. As we said, x, what is x going to here? We're trying to let it go to infinity. That is unbounded. The second type occurs when there's a point of discontinuity, or it could be a line of discontinuity. So improper integrals of type 2. Type 2. These are, and this is integration that occurs over an integral that contains a point of discontinuity. Forgotten I. So just to illustrate examples of both of these, type 1, we could see something where we want to find this area. Like I said, very similar to the first example where we just have that infinity, something running off to infinity. Notice it could be going to infinity both left and right, so let me just change it slightly. Draw a second arrow on there. So here we have it going to infinity both left and right. It's running off to infinities, yet it still may have a finite area. Type 2 might see something that looks like this. We have a discontinuity at whatever point this would be, say it's 1. And so because of that discontinuity, we can't integrate from, say, negative infinity to infinity, or even from a negative b to a c, but we could integrate from negative b to whatever that point of discontinuity is. I'll call it a, and then from a to c, we may be able to do that and to be able to get an area. So there's three things we need to keep in mind for each of these types of, for each of these improper integrals. On type 1 improper integrals, if our f of x is continuous on a to b, sorry, let me change that. If the f of x is continuous on a to infinity, because we're running off to infinity on these, not to just a set value, then the integral of a to the infinity f of x, we wouldn't want to write it with that infinity up there. We're going to instead have to use a limit. We're going to use a limit as b goes to infinity of the integral from a to b. We can't plug in an infinity into an integral. So we're going to plug in another value of b, and then we're going to say let that b run off to infinity. If f of x is continuous on some integral, say negative infinity to b, negative infinity should be in a parenthesis, then we can integrate from negative infinity to b of f of x, but we can't plug in that negative infinity. So what that means is we have to take the limit as, we'll call this variable a, not x, but a, as a goes to negative infinity of the integral of a to b f of x dx. We're just using another placeholder, a, b, c, whatever you want to call it. We're using another placeholder to represent that infinity so that we can take the limit separately. What if both ends are going off to infinity? If f of x is continuous on negative infinity to infinity, and we're trying to find the integral from negative infinity to infinity of f of x dx, we can't plug in those infinities. Well, what we can do is we can break it up a little bit. We can express it as the integral from negative infinity to a set value of, we'll call it c, f of x dx. We can add that to the integral from c to infinity of f of x dx. And so then these are back to what we did in steps 1 and 2. We have the integral from negative infinity to a set value like we did in 2, and then from a set value to infinity. So then we're back to just using parts A, or parts 1 and 2. Then use 1 and 2. So we first need to write these infinities as two different integrals, because we can't just say let's go from a to b and then let a go to infinity, and because we're going to do two different places, we have to break it up as two different integrals first. Now for our type 2, let's see what we're going to do there. First, if f of x is continuous on an interval from a to b, and discontinuous at a, so notice in the first set of parentheses and brackets I did not include the a, then we can express the integral from a to b of f of x dx by taking the limit as c goes to a from the right of the integral from c to b of f of x dx. Why are we doing this? Because if we have that discontinuity like we did in this picture, I can't go plugging in that a, right? That a is impossible for me to plug in because it's going to result in me getting a value of infinity, and infinity is meaningless. So what we're going to do is we're going to instead use a different value c, and we're going to see what happens to the limit as we get really, really close to that a value. We're going to use a similar trick depending on where that discontinuity falls. So if f of x is continuous on an interval a included to b not, and meaning it's discontinuous at that b, and discontinuous at b, then we can express the integral from a to b of f of x dx using a limit statement saying let the c get close to b from the left, approach it from the side that it is continuous on, and then we're going to take our integral. Need my eraser to come up here. There we go. It's working again. Then we're going to take our integral from a to c of f of x dx. We're letting this variable replace the problem, right? Doesn't matter if that problem is infinity or if it's giving us a discontinuity. We're using this letter placeholder to represent that problem, and we're going to take the limit as we get close to that problem. And finally, if f of x is discontinuous at C, where the C is between our A and B, and continuous for all other points on the interval from A to B. Then we can express this integral from A to B, which includes the discontinuity at C, by breaking it up as the integral from A to C, f of x dx, plus the integral from C to B, fx dx, and then using 1 and 2. So doing kind of the same thing we did with that type 1, where we say, hey, this C is a problem, so let's use some other placeholder. We'll call it D or whatever we want. We're going to get from A to D, and we're going to let that limit as D goes to C from the left, and then we'll let the E or whatever we would call it approach from the right. Just kind of using that external variable as a placeholder till we can eliminate that problem and work around it. In each case, doesn't matter for type 1, type 2, in each case, if the limit exists, and is finite, we say the improper integral converges. So if that limit that we're taking, when we break these things apart and replace it with that other variable, it doesn't matter type 1 or type 2, if we take that limit and we can find it, it is finite, it exists, we say it converges. And the value of the improper integral is the value of the limit. So whatever we get for that limit is the actual value of the improper integral. If the limit fails to exist, the integral diverges. Meaning that we can't find that area, because it could be that if something is going off to infinity just too quickly, right? If we maybe are approaching that asymptote at such a rate that it just becomes unbounded, well, that area is just going to continue to grow and grow and grow, and so it might be that we can't actually find the area under that curve as it shoots off to infinity. That does happen. So we're not saying every single improper integral is possible. We're saying some of them diverge, which means we can't find that area. It's not a finite number. That area continues to grow more and more and more. So let's do a couple examples with these. Let's see what we're doing. We've already done one example. We said it is type 1, but let's do another example. So let's take the integral from negative infinity to infinity of dx over x squared plus 4. All right, so the first thing I realize here is that we're running off to infinity on both ends, so I need to break this integral up into two integrals and choose just some value to break it up around. Now, I've chosen 0. Why might I choose 0? Well, 0 is one of the easiest numbers to plug into in 4. So 0 is very, very easy to evaluate at. It's always a good one to break it up if the ends are going to negative infinity to infinity. But notice, we don't have to. We could have gone from negative infinity to negative 5, and then negative 5 to 0 to infinity. As long as we're covering that entire region, we can break it up however we want to. It's just the zeros tend to be much easier. Now we're going to have to use some limit statements. So we're going to say, let's take the limit as, we'll call it a goes to negative infinity, and I'll go from a to 0 my integral, dx over x squared plus 4. I can't plug in infinity, but I can plug in a a letter A, that's fine. And then on the other one, because A is already restricted to going to negative infinity, I'll use B here. I'll say let's let B go to infinity, and this integral will take 0 to B dx over x squared plus 4. Could have used any letters I wanted there. I just need them to represent a fixed value that we were going to then approach through a limit. Or that we're going to let that fixed value then approach infinity using our limit, I should say. All right, so now I'm going to do my integral, but I still have my limit in front. I have to do that integral first. So if we think about the antiderivative of 1 over x squared plus 4, well, this is actually going to be our inverse tangent. And so we will have the inverse tangent, typically dx over x squared plus, this would be a 1. So that means I'm going to have a tangent, inverse tangent of x over 2 to get the x squared plus 4. But that would also mean that I'd have a coefficient of 1/2. And then we're going to evaluate that from a to 0. We'll have the limit as b goes to infinity. Well, this one's going to have to be the same, 1 over x squared plus 4. That's going to also be the inverse tangent of x over 2, but I'm going to have that coefficient of 1/2 in front because of my a value here. And so notice we can pull the 1/2 to the front just to make our life a little bit easier. And then we'll have the limit as a approaches negative infinity of tangent, inverse tangent, of 0 over 2 minus the tangent, inverse tangent of a over 2. And then we'll have our second limit plus the limit as b goes to infinity of the tangent of, and I forgot to write what we were evaluating here, we're evaluating it from 0 to b, tangent of b over 2 minus the tangent 0 over 2. And so let's simplify the zeros first. If we think about when tangent is equal to 0, that occurs at 0. And remember, inverse tangent, we have the restricted domain from negative pi over 2 to pi over 2. So when is tangent equal to 0? That is just at 0. And make sure I keep the parentheses. Yeah, that's right. And we'll have the limit as b goes to positive infinity of b inverse tangent of b over 2 minus, again, that has to just be a 0 there. So now we need to think about plugging in those infinities. If the values are getting larger and larger for tangent, where is tangent getting larger and larger? That occurs at a value of pi over 2. This one was negative, so I need to make sure I'm doing it the right way. Those values are going to negative infinity, so where does that occur? That occurs at a negative pi over 2. Those values are really getting smaller and smaller. I tried to squeeze that negative in there and I left it. I forgot about it, but remember we had that negative pi. There we go. So if I'm going to negative pi, where are the values getting smaller and smaller? At the negative pi over 2. And then over here, tangent of infinity, well, where does tangent go off to infinity? That occurs at the pi over 2. And so we'll have 1/2 pi over 2 plus pi over 2 is pi, and so we get pi over 2 as our answer. So we can say that this integral converges. The integral converges. And we know it's equal to the pi over 2. Let's take another example. Let's take the integral from 0 to 4 dx over x x minus 2 cubed. And so I'm going to start by thinking about, does this have any discontinuities? And yes, it does, right? If x is equal to 2, that denominator becomes 0, meaning we have an asymptote at 0. So the first thing that I need to, at 2 rather, first thing I need to do is I need to break this up into two integrals at the discontinuity. I'm going to go from 0 to 2 and then from 2 to 4. And so now we need to take the antiderivative of each of the, I need to back up a step. I can't leave that 2 there because doing so, I would have 0 in the denominator. I can't find that value. If I were to do the antiderivative and plug in, I would have a problem. I have that discontinuity. So I'm going to let something replace that 2 for a minute. And let's just use c. So I'm going to take the limit as c goes to 2 from the left, because we can find that one-side limit of the integral of 0 to c dx over x minus 2 cubed plus, and then here I'm going to have to take the limit as c goes to 2 from the right of c to 4 dx over x minus 2 to the third. And now that I have that replaced with the c, I can integrate from 0 to c because c is just a fixed value short of the 2. And so when we go to take our antiderivative, we'd have x minus 2 to the negative 2, meaning we need a negative 1/2 coefficient. Dx, no more dx, sorry, I need the 0 to c. And the other thing I need is, and I cannot forget it, I must have it still, I need that limit statement. If I drop that limit statement, I've made a huge error. I need to have that limit statement still because we have not evaluated that at all. And then I'm going to add to that the limit as c goes to 2 from the right of, this will be the same exact thing. We'll have negative 1/2 x minus 2 to the negative 2. But we're going to evaluate this one from, this should have been 0 to c, and this one should be c to 4. And so let's go ahead and plug in. I'm going to go ahead and factor off the negative 1/2 just to make my life a little bit easier, kind of the same trick I used in the last example. So we'll have the limit as c goes to 2 from the left of c minus 2 to the negative 2 minus 0 minus 2 to the negative 2 plus the limit as c goes to 2 from the right of 4 minus 2 to the negative 2 minus c minus 2 to the negative 2. So we can do a little simplification here if we want to, but let's think about what happens with these limits. Well, we'd have the limit as c goes to 2 from the left, meaning we're getting infinitely close to 2 on the left. Well, that thing is going to, if we think about positive or negative infinity, 1.9 would be a negative, and then because we're squaring, it's going to be going to positive. That thing is going to a positive infinity. This 2 here is going to negative 1/4, but that doesn't matter because what we see are these other things are going to infinities. And so for that reason, this would be 2 to the negative 2 minus infinity. We have a problem because we cannot find these limits. These limits are diverging because they're going to the infinities. 2 minus 2 is 0 because it's in the denominator. They're going to the infinities. And so for that reason, this limit fails to exist, meaning this integral diverges. When we went to plug that 2 in, it was still a problem after taking the antiderivative. We still are going to infinity, and so because we're going to infinity, we cannot actually evaluate that limit, and our limit is diverging. Therefore, we have to say the integral diverges, and that's all we can do with it. So let's talk about this idea of convergence and divergence a little bit more. Let's think if we can determine when integrals converge and when they diverge. When do integrals diverge? Well, let's start with this question. For which values of p does the integral 1 to infinity of dx over x to the p converge? Well, let's take this thing and let's write it in terms of our improper integral. So that means we're going to take a limit, and I'll call it whatever, b goes to infinity of 1 to b dx over x to the p, and let's see what this gives us. We need to write our limit. We have to keep those limit statements. We can't bring the infinities into the integral. We have to write those limit statements. And I'm going to take the antiderivative of x to the p, so we'd have x to the p plus 1. It is a negative p because it's in the denominator. Negative p plus 1, we step that exponent up by 1. And that means we also have to divide it by negative p plus 1, or we could have a coefficient of 1 over negative p plus 1. And we're going to evaluate that from 1 to b. And so we'll plug in. We'll have the limit as b goes to infinity of b to the negative p plus 1 over, and let me just go and pull that negative p plus 1 outside, because that's just a constant, right? It's just a constant. And then here we would have negative b plus 1, b to the negative p plus 1, and then we'd have 1 to the negative p plus 1. And if we think about what that looks like, 1 to any power is just always 1. So we can express that as limit as b goes to infinity of b to the negative p plus 1 minus 1. So let's think about when our p is greater than greater than 1. If p is greater than 1, that would mean that this number right here becomes a negative. We'd have b to the negative power. So if b is going to infinity, and it's in the denominator because this is negative, well, that means that this piece here is going to 0. So if p is greater than 1, b to the negative p plus 1 is going to 0, meaning we would be left with a 1 over negative p plus 1 times a negative 1, I should say the integral, and we would get a 1 over p minus 1. So if p is greater than 1, then the integral is equal to this. It converges. What if p is less than 1? Well, if p is less than 1, then this thing right here becomes a really large positive number. That b is going off to infinity. That means the integral diverges. And that leaves the case if p is equal to 1. If p is equal to 1, we get b to the 0 power, which that becomes a more challenging limit to find, because then we have infinity to the 0 power, which is an indeterminate form. So let's take that and play with that for a minute. If p is equal to 1, then we have the integral from 1 to infinity of dx over x, because remember what we're dealing with here is this integral right here. So we'd have the integral of dx over x, which we still need to be able to write that as the improper integral. So let's say b goes to infinity, and we're taking the integral from 1 to b, dx over x. And so we'd have the limit, b goes to infinity, of the natural log of the absolute value of x. We're evaluating that from 1 to b. So we'd have the limit as b goes to infinity of the natural log of b, and because it's going to positive infinity, we don't have to think about the absolute values for a real long time, minus the natural log of 1. Natural log of 1 is just 0, so we're left with the natural log of b, and as b goes to infinity, that means that our integral is diverging. The integral diverges. So the only time that this initial statement is converging, the dx over x to the p, the only time that converges is if the p is greater than 1. When that p value is greater than 1, that fraction will actually converge. Otherwise, it is going to diverge. So the integral from 1 to infinity dx over x to the p converges if and only if p is greater than 1 and its value is 1 over p minus 1. So this gives us a nice known fact to work with our integral convergence. And so we can think about problems like this in generality. But what if we can't actually compute the integral? Because there are going to be some problems, like we've already seen, where we can't compute the integral. Well, in these cases, we're going to use some tests. We're going to use some comparison tests to tell us if an integral converges or if it diverges. We aren't actually going to be able to compute the area. We're not going to be able to compute those integrals, but knowing whether something exists or not is oftentimes more valuable than being able to tell what exactly it is. Because if we can right away eliminate something as not existing, well, there's no sense in us spending all this time and effort trying to figure out a way to make it happen. If we don't know how to compute the integral, but we can say the integral doesn't exist, then why are we going to spend all our time trying to compute that integral? So let's talk about these tests and their theorems. So the first one is the direct comparison test. So the direct comparison test states, let f and g be continuous on the interval. Integrals and intervals tend to blend together on the interval a to infinity with the function f being larger than 0 but also smaller than g. So g is the dominant function here. Then one of two things has to be true. If the integral from a to infinity of g of x dx converges, so too does the integral from a to infinity of f of x dx. And then the other thing we know is if the integral from a to infinity of f of x dx diverges, so too does the integral from a to infinity of gx dx. I'm not going to do the formal proofs of these, but I'm going to give you the visualization for why they are true. So we are told that we have two functions, f and g. F is always less than g, or they could be equal to at some points, that's fine. Whatever they look like, they could go on forever. We're taking the integral from a to infinity. Well, if g at some point is coming back and converging in some way, so this line right now does not appear to, but right is continuing on, so it's coming back and converging. Well, if g is converging and they're both greater than 0, well then that means f of x also has to converge. G of x is bigger and it's converging, that means the smaller thing also has to be being smashed down. But if that f of x is diverging, meaning it's getting bigger and bigger, so that area is growing more and more and more, and the g of x has to be larger, that means the g of x also has to be diverging. They're gonna the bigger function can restrict or limit that smaller function, or the smaller function can grow at such a way it has to, if it's blowing up, that larger function has to blow up as well. Now, notice, what does it say if g of x diverges? Nothing. If the g of x is diverging, well then f of x is smaller. F of x could be converging down still, and the g of x could still be blowing up. Or if the f of x is converging, well, g of x could be diverging, we don't know, right? So we only have the one-way limit on this. If the larger function is converging, the smaller function converges. If the smaller function diverges, the larger function diverges. And also notice what we were saying is that these functions had to be greater than 0, because we have to have that other binding function. G of x and 0 are forcing that f of x into converging. Honestly, it wouldn't matter if the f of x was greater than 0, if the f of x was blowing up, and the larger function would also have to blow up too. But that is something we need to consider. We need to consider, are these functions greater than 0 in order to use this test? Let's talk about the next theorem. This is the limit comparison test. The limit comparison test states if f of x and g of x are positive continuous functions. Yes, we have that positive again. We've not written it in terms of being greater than 0 because we don't need one to be larger than the other, but they're positive continuous functions on our interval from a to infinity. And if the limit as x goes to infinity of f of x over g of x is equal to c, is equal to, let's say, some L value, I'll call it L for limit value. If it's equal to some limit value L, and that L is between 0 and infinity, then the integral of f of x from a to infinity and the integral of g of x from a to infinity both converge or both diverge. So here we don't need to know that one function is greater or smaller than the other. We need to know the functions are positive, that they're continuous. Those are required. They are doing this, if they are both positive and continuous and we find that limit value is between 0 and infinity, that means they're doing the same thing. If we think about why that would be, well, if they're, this one's harder for me to draw out, maybe I'll just talk about it. If the functions are both converging, or if we get a limit value out of this, if by dividing the two functions they're getting a limit value, that means they have some amount of control on each other. Some elements of them are canceling out. They are simplifying with each other in some way. And the only way that happens is if they're both controlled by some larger factors, or they're both converging into the same points, or if they're both uncontrolled, meaning they're both diverging out to some point. Notice if we have the limit values equal to 0 or infinity, that doesn't tell us anything. If it's going to 0, that means that the g is larger than the f, right? G is growing larger than the f. And so we don't have any way of comparing the two things. This is a limit comparison test. If we can't compare them through that ratio, then we don't know. Or if it's going to infinity, that means f of x is growing much, much faster. So again, we can't control them in any way. No, so I was saying the g of x or f of x is bigger or smaller. That is true over the long haul. If we were to say the f of x is always greater than g of x and f of x converge, well then we're back up to this comparison test. We wouldn't need the limit comparison test. If we can look at the functions and know which one is larger, which one is smaller, probably going to be better off with our direct comparison test. But if we can't get that order of f and g, well, then it might be that limit comparison test is easier. So let's take some examples with these problems, with these ideas, I should say. Let's take the integral of 1 to infinity 1 over 3 to the x plus e to the x dx. Now, I'm only looking at a single function here, so I get to choose that second function in a way that's going to help me. So if I can think of a way that I could maybe compare these through a limit comparison, if I could divide one function by another function and figure out what that limit value is equal to, that could be useful. Or if I could think of a bigger small function that will converge or a smaller function that will diverge, that would be helpful. So the first thing that I'm going to kind of do is think about whether I think this is going to converge or diverge. And I think there's a good chance that it might in fact converge, because we've seen how when that stuff is in the denominator is getting smaller very, very quickly, kind of like that very first problem we did, 1 over e to the x or e to the negative 1, that was converging, and so there's a good chance this might converge. So if I think it's going to converge, I'm going to look for something bigger. I want to find a larger function. And so what I know is I also want to simplify this function in my comparison. And so I'd really like to choose just part of this, say the e to the x. And what I also know is if I'm adding things to the denominator, making the denominator bigger, that makes the fraction as a whole smaller. I can take this a step backwards, and I think as we're going to infinity, we would all agree that this statement is true. If I had e to the x is equal to e to the x, that's a true statement. So by adding something here, this side is bigger. Once I use their reciprocals, that is now smaller. So I know a few things now. I have two functions that I'm comparing. I know which one is larger. I also know that this thing is greater than 0 because we're starting at 1 and going to infinity. So this has to be positive, this has to be positive. So I can apply the limit, the direct comparison test. I'm going to apply the direct comparison test, abbreviated DCT. We do need to make sure that those conditions are satisfied. We need to make sure for the direct that we are in fact sure that it's greater than 0 and that we have a larger function. Or if we're to use a smaller function to try to show it's diverging, we would need to make sure it's smaller. If we're to use the limit comparison test, we need to make sure that we're showing that the function is positive and that it is continuous. So let's apply the direct comparison test. So what this means is I'm only going to consider the integral 1 to infinity of 1 over e to the x dx. Which means I need to write this as a limit as, say, a goes to infinity of the integral 1 to a, 1 over e to the x dx. And so we've already done a problem very similar to this, but just to work it out again, we'd have negative e to the negative x. We're taking the limit of this as a goes to infinity, and we're evaluating this from 1 to a. So we'd have the limit as a goes to negative infinity, to infinity. Sorry, let me try and clean that up a little bit so I can actually read what I'm writing. So a is going to infinity, and we would have negative e to the negative a minus e to the negative 1. So obviously the e to the negative 1 is converging, and so we just have to think about this a portion. If a is going to infinity, this piece right here is converging. It is going to 0. And so we're getting, just keep that in parentheses, e to the negative 1 here when we do this limit, which converges. And remember, we said that this function 1 over e to the x was larger than 1 over 3 to the x plus e to the x. And so because the larger piece is converging, the smaller piece must be converging as well. So because of this inequality, and it's all greater than 0, And we saw the integral of 1 to infinity of 1 over e to the x dx converges. So too does the integral from 1 to infinity of 1 over 3 to the x plus e to the x dx. Now, notice I have never stated what that integral equals. We didn't find that. We haven't found that. We're not going to find it in this problem. All we are doing is we're determining whether these things converge or diverge. We know that this area is finite because of the direct comparison test. We don't know what it is. Once we use a test, we are not saying what that limit is equal to just because the f is being controlled by this other function and we're forcing it downwards. Obviously, this area is much larger than this area down here. And so we aren't saying those two areas are equal. These comparison tests are not saying the areas are equal. We're just saying that if one thing converges, the other thing converges, the smaller thing converges, or if the larger thing, the smaller thing diverges, the larger thing diverges. I expect to see this in your answer. I expect to see a statement that says, hey, I've made sure the inequality works. I've seen that this is the larger function, this is the middle function, this is the 0 is the smallest. I've shown that that larger function converges, so too does that smaller one. Or if you're proving it the other way around, because this smaller one diverges, then this one diverges. But I expect to see this statement when you're determining whether it converges or if it diverges. Let's do another example. Let's take the integral from 1 to infinity dx over 1 plus x squared. So the first one we did with a direct comparison test, that one would have been really hard to use a limit comparison test because remember with the limit comparison, we have to divide that function by another one to get a limit value. And because I had that 3 to the x in there, that's just never going to be very easy to cancel off. So this one, let's think if there's a way that we could use the limit comparison test, just to see if we could do it. So I need something that when I divide it by the 1 over plus x squared, it doesn't matter which side you divide your functions on, but when I divide this upper function here by this other function, we have some cancelizations to where we can determine if they converge or diverge, because I need to be able to get to a limit value. That is my goal. I want to get to a limit value. If I'm getting 0 to infinity, it doesn't tell me anything. So if I were to choose something like x to the 50th up here, sure, I could find that limit, right? And that limit would be going to infinity, and that tells me nothing. So that's not useful. So I'm trying to figure out something that when I divide it, it will give me a limit value. So I'm going to choose an x squared. I'm not going to choose that. I'm going to choose a 1 over x squared. Because what I want is when I do this division, I want to have the same degree polynomial on top and bottom because that's when we get a limit value out of it. Remember, with rational functions, if we divide a polynomial by a polynomial, if those degrees match on top and bottom, then we have a limit value. So we're still letting our x go to infinity. If I multiply by the reciprocal, I would have 1 over x squared times 1 plus x squared over 1. And notice I'm getting the polynomial x squared, 1 plus x squared over x squared. And the limit of that is equal to a 1. So I'm choosing a function. In this case, I chose the 1 over x squared. I'm choosing something to give me a limit value. If I choose something that doesn't give me a limit value, all that is useless. It's not told me anything. So now I have a more simple function, 1 over x squared, that I can hopefully find the integral for. So the integral 1 to infinity, 1 over x squared dx. We first need to write that with limits. We'll call it a goes to infinity of 1 over a, 1 to a of 1 over x squared dx. And the antiderivative of that would be x to the negative 1 with a negative in front. We're evaluating that from a to 1. So we'll have the limit a goes to infinity of negative a to the negative 1 minus negative 1 to the negative 1. And we can see here as our a goes to infinity, this piece right here is going to 0. And so we are getting a set value, I don't really care what it is. It would be a -1, negative turns into a -1. I'm getting a limit value out of this, which means that our function must converge. This original integral must converge, because remember, if we have that limit value, if one converges, the other converges as well. So we need to write that up now. Because the limit as x goes to infinity, 1 over x squared over 1 over x squared plus 1, because that limit is equal to, do we say it was, 1, and 1 over x squared and 1 over x squared plus 1 are continuous. I didn't make a big deal out of that, but I do need to make sure I'm choosing continuous positive functions. We can apply the limit comparison test. We found the integral of 1 to infinity of 1 over x squared dx converges. So too must the integral of 1 over x squared plus 1 dx from 1 to infinity. This one I could have actually done a little bit more simply, because this 1 over x squared, that was that general case that we actually did a few minutes ago with the p's. Remember we said if p is greater than 1, that is a convergent function. Now that we've proven that in generality, we can use that. So I'm going to do this exact same problem again, but this time instead of using the limit comparison test, I'm going to use a direct comparison test. I'm going to use that little shortcut too, just to show you how it would work. So the direct comparison test also works on this problem. We're still trying to solve the integral from 1, or we're trying to determine the convergence of the integral from 1 to infinity of dx over 1 plus x squared. I'm going to use that 1 over x squared function again because it's a pretty easy comparison. 1 plus x squared obviously is larger than x squared, and so 1 over 1 plus x squared is smaller than 1 over x squared, and those both are clearly greater than 0. And so the integral of 1 over x squared dx from 1 to infinity converges as the p-value is greater than 1. This is that p-value problem that we tested out before. Converges as p is greater than 1. Therefore, using our direct comparison test, since 0 is less than 1 over 1 plus x squared is less than 1 over x squared, the integral from 1 to infinity of 1 over 1 plus x squared dx must converge. Let's take one last example. So let's determine the convergence of the integral of, let's take 4 to infinity of dx over the square root of x minus 1. So I have choices. I can use my direct or my limit comparison test. We've used two examples now where we did the direct comparison test. So let's try the limit comparison test again. Let's see if we can figure out something that'll work there. And I see that square root of x there, so I'm going to try to use 1 over the square root of x as my comparison. And so I'm going to take the limit as x goes to infinity of 1 over the square root of x over 1 over the square root of x minus 1. So we can simplify, and we'd have the square root of x minus 1 over the square root of x, and that limit is equal to 1. And so we've now shown that the limit value exists of their comparison, of their ratio. I should also note that these functions are continuous. 1 over the square root of x and 1 over the square root of x minus 1, are continuous on the interval. Are they continuous from negative infinity to infinity? No, they aren't, but we're going from 4 to infinity. So on the interval, they are continuous. And they are also both positive. I should just add that in there, positive. Would it be positive from 0 to infinity? No, it wouldn't. That wouldn't be. But on the interval that we are concerned about, yes, they are. So I can apply my limit comparison test. So I'm going to look at the integral from 4 to infinity of 1 over the square root of x dx. Using that same p test that we dealt with a second ago, or the same ideas of p, this is an example where p is equal to 1/2, which is less than 1, which tells us this integral must be divergent. Therefore, using the limit comparison test, since 1 over the square root of x and 1 over the square root of x minus 1 are positive continuous functions, and the limit of their ratio, 1 over square root of x over 1 over the square root of x minus 1, is equal to the limit value of 1, we know, there's one other thing I need to state. That all sets up the conditions of the limit comparison test being true. The limit comparison test tells us the integral 4 to infinity 1 over square root of x minus 1 diverges since the integral from 4 to infinity of 1 over the square root of x dx diverged. And so that is a complete answer. We have shown that the conditions that are true to use a comparison test have been met. We have shown that the integral we're comparing it to either converges or diverges. Then we make our final assessment. In this case, that our integral was in fact diverging.